So let's move on. Let's talk about the Holt-Winters method. So as I mentioned, right, the principle behind Holt-Winters method is it separates out the time series into these three components. Okay, we already talked about these three components that are there as trend, seasonality, and error part. And as you rightly pointed out, what happens is in the literature, as far as Holt-Winters is concerned, they talk about these three components as instead of trend, seasonality, and error, they call it as trend, seasonality, and base level. So in my mind, the distinction is not very major. So what it does is basically this. You have, let's say, a time series that looks like this. Okay, it starts from 200 and goes to 400 something, right? There are multiple ways to split this into these three components, and of course, let's put in the error there, right? This error is also there. So the ways you can split this up is you can talk about this as this trend, and there's this part which is this oscillation that is there, and the error part is this small oscillations that are there, right? The thing is, you can put this, the sum of these three need to be this time series, but there is no clarity onto where to put this level 200. The size of the 200, you can do it multiple ways. You can set the trend to start from 200 and go all the way to 400. That's one way to do it. An equivalent way to do it would also be to start it at 0 and go till 200 and have this to be at the error to be oscillating around the level of 200, right? All we are talking about is where are we pushing that intercept, the best fit intercept, into which portion. They're all equivalent ways of doing it. The way I would like you to think about this is as they're talking about as a base level. Instead of calling it as an error, they call it as a base level. Essentially, the base level has components that are other than pure trend and pure seasonality in the series. Okay, and what they do here is this. They say that your time series, the total time series, is split into the base level or error, as we called it before, trend, and seasonality, summation of all three of them. Now, they are going to get the forecast of time t from the value at time t minus 1 of the base level, time t minus 1 of the trend. The seasonality part, they are going to get it from previous period, whatever was the value. So t minus p, right? Because seasonal part is the periodic part, right? So you can get that number. That's what this is giving you. Each one, however, is separately evolved through a exponential moving average process. And each one is evolved with an exponential moving average process with separate coefficient for that particular thing, that particular quantity. What we talked about before was the entire time series, we decided to fit it with one alpha value or one moving average window, one exponential moving average window. We try to find the the parameter that minimizes the error, right? What we are doing here is we are separating it out into three portions: uh, the base level, the trend, and seasonality. And we find the best window, exponential moving average parameter for each one separately. So we are increasing the number of parameters for fit to 3. Okay. Obviously, I mean, when you have larger number of parameters to fit, you can perhaps do a better fit, is the idea behind the thing. And each of this process, I want you to just focus on the structure of the equation. The exponential moving average process is evolved through a parameter alpha. The trend parameter is evolved through a parameter beta. And the seasonality parameter part is evolved through a parameter gamma. And in each one of the cases, it depends on the previous value. So the previous value is weighted accordingly, right? Underlying what's happening is 3 separate exponential moving average processes that are happening. Of this, we talked about there are 2 kinds of seasonalities we can think of: additive seasonality, multiplicative seasonality. The only difference between the way additive seasonality is implemented versus multiplicative seasonality is implemented is in additive seasonality, you have these 3 terms adding. In multiplicative seasonality, the seasonality term comes in as a factor that's multiplying these. Okay. This is what we talked about as multiplicative seasonality. The seasonality as a factor that's multiplying whatever is the forecast that is done by other means. Previously, we talked about a linear forecast and we adjusted it by a factor. Here it is a exponential moving average forecast and that's adjusted by a factor. Yeah? Intuitively, that's what is happening. 3 separate moving averages evolving these 3 time series, which we showed initially. Any time series we talked about as being able to be can be split into these 3 components, and we are evolving each one of these components separately. Let me show you how it's run on R. So Holt-Winters forecast is done through the command Holt-Winters, and I said there are 3 parameters: alpha, beta, gamma. Alpha was for the level or the error part, right? And the beta and gamma was for the trend and seasonality part. What I'm going to do is first try to do Holt-Winters forecast by setting beta as false, gamma as false, which means I'm saying use only alpha. So I'm saying use only as if treat only the random component or the level component. Do not use the trend component of the data at all. Treat it as if it's got only the random component or the level component and forecast it. So forecasting, as I said, is an exponential moving average forecast, right? So let's see how it looks. When I run this, so The black line is the actual data, the birth New York birth series data, and this red line is the forecast by Holt Winters. See what it's doing. The value as the birth dipped, the value of the time series or the forecasted value is higher than this, right? Why was it higher? Because what it does is, in order to make forecast at this time, it used the previous values and effectively took an average of the previous values. The previous values are all higher, right? So previous values are all higher. So the average of that number is going to be high. So at this time, it gave that value, right? What you see effectively is this ups and downs are there, but these ups and downs are lagging behind the actual data. Okay, it's almost as if you take this black line and shift it slightly. So after a dip happens, few months after the actual dip happened, the red line will show a dip. Few months after the actual high happened, the red line will show a high. That is a very typical characteristic of any moving average forecast. Moving average forecast introduces lag in the data. Okay, so when you try to use moving average forecast for predicting a seasonal number, moving average forecast will show a lag in the seasonality. So we didn't use seasonality in this forecast. We used only the random level into the forecast. So it gave a poor forecast. Let's see what happens if we allowed for seasonality. Yeah. So what it's trying to do is, in this case, it's trying to extract out the non-seasonal part. Y minus removing the seasonal part. This is the non-seasonal part, and this is the trend part. What it's trying to do is trying to do an average of the non-seasonal part and the part explicitly from the trend, and that's what it's trying to give as a base level. We can plot and look at the individual levels here. One second. So over here, what I have when I'm setting use the Holt Winters to make the prediction, I told it that do not use beta and gamma for the forecast. Use only alpha value. So use only a moving average process. Do not take into account any of the seasonality part, right? So it's giving me only alpha value. This is the best fit parameter it did. Essentially, it did a parameter search and found out this is the best value of parameter that makes a fit, good fit for this particular problem. We need to, in order to get the seasonality part, we need to do with the full one. Yes. So in this case, I'm doing a full seasonality. I'm not specifying use only. I'm asking it to use all three values, and here the forecast now gives you all the parameters, all the fitted parameters. Each one, the level is being smooth with this parameter, the trend with one, and the seasonality with the other one. Okay. And since seasonality, what is the seasonality in this time series? This is the birth time series, right? What is the period length? 12 months was this thing. So in order to forecast for February, the seasonality component will take into account values from last February. For January, it will take values from the last January, and so on. Each one of the months will therefore have it fitted with a different set of coefficients. So you see 12 coefficients that are corresponding to each one of those months. Ultimately, in order to make the forecast, you forecast through forecast.hold pointers. In this case, I'm forecasting for 8 periods ahead. So when I use the hold pointers, all the seasonality, everything, and asking it to forecast, it has taken into account trend. So it's giving me a forecast that is continuing to increase along with this base level, right? And it also has this trend, this seasonal variation is also captured. So putting three separate parameters instead of just using one parameter has some benefits. You're able to model seasonality separately. You're able to model trend separately, and the base level as well. This is the uh, first level of complicated useful method that you actually are going to potentially will be using in time series forecasting. Most of the simple moving average methods would not give the desired level of accuracy typically in any real series. If you're doing simple, 3 quarters or 4 quarters of data you're trying to forecast the first quarter, it's okay to use any of the simple moving average methods. But any real data with any level of seasonality, you need to start going into this hold pointers method. So first real method with seasonality built in is this. Yeah, correct. So each one is a separate window length, separate window size for one for error level, the other one was trend, and seasonality. It fits best value parameters for each of those components separately rather than trying to fit for the entire time series at one stretch. And philosophically, you're increasing the parameter size, so you probably end up with a better fit because of that. But you're choosing these parameters wisely. In that one, you are separately forecasting trends, separately forecasting seasonality. When you are able to separate it out, your hope is that you'll be able to do better forecasts. And it does turn out that you end up doing better forecasts. Yeah, yeah. So um, any of these stock data, these methods do not work, right? Because imagine, right? You pay 3 lakhs for the course and you'll make 1 crore or 2 months after the course. It doesn't. It's not going to be a value proposition for the people who are teaching it. So, uh, uh, turns out stock data do not have any seasonality. Um, I if you find a stock which is stock data which has got some known seasonality, do let me know as well. uh, you need you end up needing more complicated methods, and the level of errors that we are talking about. Here you did this your accuracy computations that we are doing. You are it's about 10% kind of accuracy. Error size is about 10-15%. In stock data forecasting, I'm not even trying to forecast whether it's going to, what the actual stock price is going to be, right? That's what we are attempting to do here, forecasting a value. I just forecast whether it's an up move or a down move. And on that, my accuracy is about 52%, right? If I use coin toss, I get 50%. So my edge is 2%, right? And people make millions if you have a 2% reliable edge. Um, so the it's very hard to find edges which are greater than that. So none of these methods will work for your G stock data or any of the other stock data. So I can we can talk about how to do that after that's getting little too technical for it. That's a good question. Um, your if you have daily data, but seasonality is only seen on a monthly level, how do you handle it? You can aggregate it at month level, one way to do it, but there are also other methods to do it. I can send you links on how you can do it. Yeah, but it gets little complicated for what we are talking about here. So let's see about Holt Winters. We go back to our original, the first problem we talked about, right? The sales figures from this fictional company. What happens when you use Holt Winters? Um, so we built the model by hand. If you remember what we did, right? We did a quadratic fit on this, and we put quarters as a separate predictors in that. With Holt Winters, you don't need to do any of that. You give the time series into it. It automatically, since it internally splits it into trend component and seasonal component, and it fits the trend part and seasonal part separately using different parameters for it. So it will do all of that automatically. So as I said, this is the first real model that you potentially going to be using. Right? All of the other models we have talked about till now is just introduction leading up to this model. For the Holt Winters seasonal one, do you think this would be an additive time series, additive seasonality, or multiplicative seasonality? How does it look? The oscillation, does it look like it might be multiplicative or additive? Multiplicative. Last time when we showed this picture, our eyes wasn't trained to spot this. Now we know, as the size of this seasonal variation increases with the value of y, that's multiplicative seasonality, right? So Holt Winters allows you to do both additive and multiplicative. When you do additive seasonality, the sum of squared error turns out to be this big number. When you do multiplicative seasonality, the fit turns out to be much better, and the sum of square errors is lower as well. Okay. We are. This is what we talked about. Holt Winters for the birth time series using only randomness, and Holt Winters using all the components. When you explicitly allow for seasonal components to be fit to, the fit turns out to be much better, as opposed to when I just used a simple moving average to fit. So Holt Winters, if I split it into seasonal trend and then do moving average on the components, you get a much better fit. I showed you this graph as well. If you after you fit, you can forecast out for n time periods using forecast.holtwinters command, and with the forecasting it does also shows that seasonal impact. The orange line shows the confidence, the prediction, 95% prediction interval. That's what it shows, or 2 standard deviation values. That is a very good question. So as you forecast the size of the standard deviation, you would see that the forecasting error would also increase. The moment your forecasting error touches the order of magnitude of your time series, then it means you no longer have any value. So it's a heuristic way of doing it. The size of the error, which is also going to be printed out along with your forecast, once the size of the error reaches the overall range of your time series, it means you no longer have any valuable information. Yeah, I mean, variety of such heuristics could be used. It depends on your business use, what level of accuracy you need. The nice thing is you the level of uncertainty in your forecast is given to you. So you are able to make a decision whether it's good enough for your application or not. Once you have done the forecast, yeah. So this model will not give you lag if you use all of the values. Uh, so, so this Holt Winters, I'm using only the random part to forecast. So that gave the lag. When I use all of them, what it does internally is exactly what you said. It uses decompose command to split all three of them, and each one it evolves separately using an exponential process and then adds it up. And here you see there is not a lag. There's no lag on this at all. So when you use all three components together, the lag is removed. Once you fit it, when you did in linear regression, after a fit, we looked at the residual, right? Same thing we do here too. Once you have done with the fit, the residuals are output, and the residuals, just as before, you don't want to see any patterns in the residuals, right? If the residual has a pattern, it means you still have information in it that can be extracted. So more processing can be done before better forecast can be done. That's what it means. So how do you check? Previously, when we did linear regression, the order of the residual points didn't matter at all, right? The one row, you could have exchanged the rows and still you would have got exactly same fit. The order of the points had no significance at all when you did linear regression. Only the x value and y value, as long as the pairs are maintained, the order in which you supply the points didn't matter. But the whole thing in time series is the order matters here, right? So when you are analyzing the residuals, what you are explicitly looking for is the order. There will be no order between one point and its next point, or in other words, there is no autocorrelation in the residual. That is what you're checking. So what I've done here is I've taken the residual values and send them into an autocorrelation plot. In this case, it's a partial autocorrelation plot. And when no values exceed the threshold, then you say that all information has been extracted. In this case, there seems to be some residual information that is still left. So perhaps there is a better method than Holt Winters that can be applied to extract better predictions. Holt Winters can do only this much, and we'll be talking about are there any better methods which can extract this. What does this tell you? Is a trend has been left behind, or what has been left behind? Some seasonal component has been left behind. Seasonality has not been fully extracted. That's what it's telling you here, right? So there could be a new method which can potentially extract that information too and make better forecasts. And we'll talk about what is that better method in the next minute or two. Any idea? Any questions before we move on to the next method? Okay. Okay. So the next method, I promised that we'll introduce two methods, two gold standard methods that are used for real data. Holt Winters was one. The other method we are going to be talking about is called ARIMA model. Okay. So we talked about how we are trying to make the forecast using only past data. So we talked about y of t plus 1 is being forecasted by y of t minus 1, y of t minus 2, so on, some as a function of that. what we are going to do is try the simplest one that one can do with this, which is a linear model. So I am going to look at y of t plus 1 as a1 times y of t plus a2 times y of t minus 1, a3 times y of t minus 2. In other words, I have sales data here, y of t. So it's 30, 25, 28, 19, 24, so on. I have sales data, yt. I am going to see if there is a connection between this data and yt minus 1 and yt minus 2. So this data is all, shifted data, right? This is shifted by one more lag. Use these two guys as a predictor and see how well I'm able to predict this. Linear regression. Two predictors and one this thing. This type of method is called as autoregressive method. As the term indicates, it's a regression that you're doing. And the word auto indicates that you're using regression using data from itself. Yeah? You will be able to do this. This will potentially lead to good results if you find that your ACF chart and your PACF chart indicates that the value with one lag and two lag are important. If your one lag and two lag are important, it means that that has enough information to try and predict about the future. So that information can be used to build a linear model. Okay, this is exactly linear regression. This is what we talked about in the first two modules. Instead of using other predictors, we are using the same data to build this. This kind of models are called as autoregressive models of order P. It's called order P when there are P terms that are used. In this case, when I'm using only two terms or three terms, this is autoregressive model of order 3. Okay. Simple linear regression is all going to happen inside with the previous terms. So the order of the model is determined by which PAF terms are non-zero. Partial autocorrelation functions, which ones are important, is going to determine how many terms I'm going to use. I'm not going to do any examples for this because we are building one step at a time, right? So this is autoregressive models of order P. There is another type of models called moving average models. Moving average model, particularly exponential moving average model, how did we make the prediction? We were using the previous value and correcting it by the error, right? That was what your exponential moving average did. This moving average model uses the same philosophy, except instead of restricting yourself to the error made in my recent term, I use the error made in my previous terms too. That also has information, right? So if I use the previous, the most recent error and the previous error, then this would be called as the moving average of order 2. The number of error terms determines the order of the model. Do you see that this is exponential moving average? Exponential moving average, we are adjusting the forecast by the error we made. That's what this is doing too. The error we made is used to make the most recent forecast, the current forecast. Instead of using only the most recent error, you could potentially use multiple terms of the error. Okay. The number of terms of error that can be used is determined by the ACF plot. The ACF plot actually tells you how many of those terms is appropriate for using the model. Again, I'm not going to do an example of this. So we talked about autoregressive model, moving average model. Another class of models is when those two are combined together. They are called as ARMA models, autoregressive and moving average terms. So not complicated at all. What you're doing in this is an ARMA model of order 2, 1 just has two autoregressive terms and one error term. Okay. How would you do this in practice? Each one of them would form a column and you do a linear regression fit to try to find the best set of parameters that's going to minimize the overall error. Underlying thing is you try to find parameters that minimizes the overall error. The only question is which terms are going inside. So terms that go inside are in for a ARMA model of 2, 1, two autoregressive terms and one error term is going inside. Okay. Again, we are not going to do any examples because we are going to build some more. The last one. Oh man, I misplaced the slide. Okay. ARIMA model. ARIMA model is, all you are saying is, this stands for autoregressive integrated moving average. Where did we introduce the term integrated? Converting to stationary. So if the given time series needs to be differenced once to make it stationary, we called it integrated of order 1, right? So ARIMA model has three parameters, P, D, Q. P indicated how many autoregressive terms are used. Q indicated how many error terms are used. D indicates how many times you need to difference it to make it stationary. So if the given time series needs to be differenced twice to make it stationary, then this term D would be 2. If it just difference once and it becomes stationary, then the D will be 1. If the given time series is already stationary, then the value of D will be 0. Okay. ARIMA models is the second set of model I told you. So gold standard models you'll be using for forecasting. Okay. Holt Winters was one, ARIMA model is the other. So P was determined from the number of non-zero terms in your PACF plot. Q was determined by the number of non-zero terms in ACF plot. D, the differencing, is something that you need to look at to find out how many order times do you need a difference to make the series stationary. Once you have chosen the value of P, D and Q, the software will enable you to do a simple linear regression in the background, fit it and give you an appropriate forecast. I'll show you how the forecast is done. Okay. So here is the time series data of number of users connected to the internet through a server every minute. Okay. This data is one of the data sets that come standard with R. So you see this kind of pattern. Starts out at 100 users, it increases to some level, then it drops, then it increases, and perhaps going through another drop. You want to make forecast of what is going to happen in the future. Okay, in order to make the forecast, you need to choose what model you are going to use to forecast. Let's say we make a decision, we are going to use ARIMA 310 model. What does that mean? It means I'm going to use 3 of the previous terms in my regression equation. Yt minus 1, t minus 2, t minus 3. I'm going to use 3 of my previous terms for making the regression. But it also has a 1 there. So it means before I start this process of regression, I'm going to difference the series once. I'm going to take the difference of the series once, create the difference series, and for the difference series, I'm going to do 3 terms and do a linear regression after that to determine the coefficient. That's what this is saying. Luckily, R has coded in all of that, and the way you fit it is you explicitly call this function ARIMA. Arima send the data set and then give the order of the model you want to fit. The order of the model is 310. I'm specifying it. And it gives a fit. I'm sending the output of the fit to this function. I can use that output of the function and forecast for five periods ahead. And over here, it's forecasted for 5 periods ahead. It's saying that for the next 5 periods, it's likely to decrease. But it has this wider and wider error range as you try to increase forecast farther and farther into the future. Okay. In this case, I randomly said that I'm going to try Arima 3,1,0 to forecast. However, the systematic way to do it would be to look at the PSEF and ACF plot and determine how many terms I need. That's a painful procedure. Luckily, R has a package which automates that too and tells you how many terms you need to use. And that's where the next slides are this thing. So the number of parameters PDQ needed to fit depends on the data set. And AutoArima is a command that automates this process, finds out how many parameters are needed by looking at the ACF plot and PSCF plot. It looks at the ACF and PSCF plot, finds out how many parameters of P are needed, how many Q are needed, and how many D are needed, and it automatically fits it. Okay, that function is available only in R. It wasn't available when I learned Arima. I had to code in all of this by hand. One of big advantages of being born later, right? So in Python, however, I'm not aware of whether such function exists or not. Since you're talking only about R, it's fine. So here is a data set. The flow of river, the volume flowing through Nile from from one city over a period of well over close to 100 years. Okay. This is another data set that's available. I don't know whether does it look like it has seasonal. There seems to be variation, but it's not clear it's actually seasonal, right? So here is the data set. The way I try to forecast using Arima is I use this command AutoArima. AutoArima, what it does, it automatically figures out how many P values you need, how many differencing you need, how many Q values you need. It fits it and it says that the best model is Arima 1,1,1, which stands for one of the autoregressive term, one error term, but one differencing needs to be done before the whole process is started. Okay, so it gives the value of this coefficient, and the way I forecast is using the forecast command, and I specify how many periods I'm trying to forecast. I'm forecasting 4 periods ahead. So in this case, what I did, I held back some data. I call this data as training, and I held back 4 points, and I made that point as last 4 points as my test. And I made AutoArima predict it, and the red value is the actual values from my test set. And what you see is that the red line lies within the error bars that were given. So the forecast given by AutoArima is not that bad at all. There was, as far as AutoArima is concerned, it didn't identify any seasonality in it. So there is a variation or the next level to Arima, which includes seasonality. And the seasonal Arima has a name called Sarima. So what Sarima does is very similar. Just as Arima had these 3 parameters, P, D, Q parameters, which identified number of autoregressive terms, number of differencing, number of error terms. It also has capital PDQ, which corresponds to how many of autoregressive terms in periodic way you take. So if this capital P is 2, it means you need 2 years, 2 February's data. Last February's data and the previous February's data. That's what this capital P, when P is 2, says 2 of previous period's data is needed. Q stands for the number of previous year's error data that you need. This number M that is there tells you the periodicity. So if you are dealing with monthly data and the seasonality turns out to be 1 year type seasonality, M will be 12, talking about the level of periodicity, and the best PDQ value will be fitted based on whether the series itself has any periodicity or not. Okay. All of this AutoArima handles, so you don't need to actually look at the ACF and PACF plot ever to figure out whether what are the right number of parameters to fix. AutoArima puts all of them together in it and makes your forecasting process easy. I'm scared to ask, is it clear? But I'll still ask it anyway. Any questions rather than is it clear? Yeah, AutoArima is a good news. Absolutely. I can tell you life was very painful before that to code, to figure out the number of parameters. But it had big advantages. When you had to do everything yourself, it means that you were looking at these charts by yourself and you understood what was happening. ACF plot and PSCF plot does have a lot of information. And anytime you are looking at it manually, you gain information, some knowledge, some experience, instead of having the computer do everything. Right? It's the same argument people make. There is some advantage to making kids doing multiplication by hand, even though it can be done by a calculator easily. You gain some number sense. But it's good news. It makes teaching relatively simple when AutoArima is there, particularly in an applied engineering class. Yeah. But very good question. And that part, I have to give you a reference to the. But again, ACF information has so it does two things underneath. It does decomposing as well to analyze what's inside. And the ACF and PACF does have that information. PACF will have values, 1 period away, and it uses that to figure it out. But it's tricky to talk about how it figures out the Q value in PACF. But I can show you a reference. Any other questions? Small PDQ and capital PDQ, everything it figures out automatically. I'll show you how the output actually looks. And the R file that I sent you, you will see the commands, and that's the most typical way you'll be using all of these functions. The theory looks complicated. It is complicated. But in terms of applying it, it's easy. It's not all that complex. Correct. 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 Right. So so this is the thing, right? We need to understand. Very, very good question. We need to understand what is predictable by time series and what is not predictable by time series, right? No matter how complicated a time series method, there is no way it could have predicted the 9/11 happening, right? That intelligence is not there in the past data. We need to see what intelligence is there in the past data, and that's the only thing that it can predict. any of that kind of political changes would most likely, it will be interesting to look at the data, but most likely show up just as 9/11 showed up in the noise factor. Any political thing like that would probably show up in the noise factor rather than in the trend part or the thing. However, the subsequent changes that happen, that will show up in the trend part. Whatever was the subsequent change, the slowing down of population growth after that, those all will definitely show up in the correct. Yeah, I'll have to see the data, but my my intuition is that um, it would show up as a noise. If you're looking at decades of data, it will show up as noise, that part. But the subsequent impact, the actual birth rates itself slowed after that. The subsequent impact, just as, after 9/11, the economy did slow up. The recovery was slower after that. The subsequent one will show in the trend itself. But that event itself might probably be show up in noise. My guess. Correct. Right. Correct. Right. Right. So that's why I'm saying it will show up as noise. It won't show up as trend, and it won't show up as how, right. So we so yeah, we can talk about that a little bit. I can talk about my experience on how I did handle my this. I mean, I faced that problem and I this thing. But let's do this at the end of the class. We'll talk about that. Let me we'll just wrap it up by just giving some examples of how using AutoArima. Okay. The here is the birth time series. Is that stationary? To me, it looks this trend. When you differencing once versus twice, um, do you think differencing once is enough, or do you have to difference twice to make it stationary? Does this look like there is trend here? To my eyes, it looks most trend has removed. To me, it doesn't seem like there is much difference between these two. So for this particular chart, I would guess that differencing once is enough. This is what I would say. When I put it on AutoArima gives the best model to fit as this 2121112. Let's start from the back here. What is this 12? Periodicity. What is the length of the period? 12 months is what it's identified as the period, right? I said we'll start from the back. I lied. Let's go here. What is this? Autoregressive terms, right? It says in order to make next month's forecast, I'm going to use this month's forecast and previous month's forecast. This one said I need a difference only once, so I'm done. This one, two error terms. The error I made this month and the error I made previous month. So AutoArima figures out how many is the optimal number of terms that are needed, and it goes ahead and it gives you the values of those coefficients. This is the coefficient that is needed for this month. I'm doing a linear regression, right? Ultimately, I'm building a linear regression. So this month's price or this month's birth value, I'm going to use one coefficient. Previous month's one, I'll have another coefficient. Those are those two coefficients it's computing. And that's the coefficient for the error terms that it's building. Okay. And it estimates all of this not through least square fit, but through a maximum likelihood estimation. Okay. And you can, again, it gives you the AIC values, which is what it uses to determine how many parameters are needed. Okay. In this case, if you try and do the forecast again respects the seasonal variation that is there. Okay. It's got the seasonal variation and it also has accounts for the trend. Okay. Holt Winters also did that. Holt Winters also accounted for the trend and also seasonal variation. This AutoArima also does that. So the time series model building general principles. Consider the model of general model of ARIMA. You need to identify the appropriate degree of differencing you need to do to make the number stationary or not. Using ACF and PACF, you typically find what is the number of parameters that you need. Okay. And you would estimate the parameters using a regression like fit. Previously, in the old world, you would identify number of parameters needed and you would use a regression like fit to identify the value of those parameters. And you perform residual analysis to make sure that all the intelligence that is there has been extracted. And then you start doing your forecasting. But all of this is encoded into AutoArima. And so it makes life simple for you. Okay. I'm giving you a link which talks about, different set of rules, how do you identify which parameters and all of that over there. But again, in practice, you just use AutoArima to make this forecast. Similarly, for the miles time series, what was interesting for me in the miles time series was this. I would have actually thought it would need differencing to make it stationary. But AutoArima says that no differencing was needed on this level, but if differencing is needed at the periodic level, it needed only one autoregressive component and only one error component on this, which was interesting. I couldn't have guessed that by looking at the data itself. In addition, AutoArima also gives a drift term. What this drift term does is it says that in addition to these forecasts, these terms for forecast, it also has plus C times D. You remember the first trend only forecasting we did? We were trying to do y of t as a function of t only. The second part we did, let's forget the t, we'll do y of t as a function of only this. AutoArima accounts for the drift term as well. And this is the coefficient of that drift term. Residual analysis, in this case, after we extract the data from the miles time series, you look at the autocorrelation and partial autocorrelation chart, and there is a way to evaluate, whether the residuals still is noise or not. There is a test called Box-Jung test, which you send the residuals into the test and it will spit out the p-value. And the p-value in this case, it says that there is a 75% probability that it's noise. There's no intelligence left. That's what the Box-Jung test does. Okay. Now, if you use forecasting data, the time series data that was the miles per the revenue miles problem, that passenger revenue miles problem, the data that was available on the for initial download was only till I think 2013 or something. Now more recent data is available. What has been done is that